Sorry for an interruption in the previous video. So I was explaining to you how do we define the model to check the doubling time, right? Given a initial quantity of a physical object, or growth of anything. It can be population of a bacteria, population of a species, human population, or anything for that matter. So if we have to calculate the size, or the time when the initial size becomes double, so we use this particular model. So to do a problem for you people, I will do an exercise problem, say problem number 2. Okay, so problem number 2, I'll read out the problem for you. A certain culture of the bacterium Rhodobacter I don't know how to spell the other one. It's a bacteria, kind of a bacteria, which initially has 25 bacteria in number. So N0 will be 25 and is observed to double every 5 hours. So the doubling time is A, right? So A is 5 hours. Okay, so and we have to for the first problem, find an exponential model n of t is equal to 2 n0 2 to the power of t over A for number of bacteria in the culture for t hours. So we just plug in all the values or all the data that we have. So n0 is 25, 2 to the power of t over 5. So this would be the model for the given problem. Okay, so second, we are asked to find out, estimate the number of bacteria after 18 hours. So 18 hours in the sense we have to estimate n of t when t is 18. That is, we have to calculate n of 18. So that would be, this is equal to 25 times 2 to the power of 18 divided by 5. So 2 to the power of 18 divided by 5 is nothing but 12.1257323. So times 25 would give me 303.1433 approximately. Okay, so 1433, this would be, that means you cannot have 1433 as as a number of bacteria. So you approximate it to say 303 in number. So after 18 hours we will have it to be 303 bacteria will be found in the whatever vessel or something. So that would be the number of bacteria after 18 hours. So next question is, you are asked to find out you are asked to find out after how many hours will the bacteria count reach 1 million. So for n of t to be equal to 1 million, okay, so if n of t is 1 million, so how long does it take for, so you have to calculate how many hours will the bacteria count reach 1 million. So you have to calculate t is what? So you use this particular model, that is part A of the solution of A to solve this. So that would be 1 million equal to 25 times 2 to the power of t by 5. Okay, so now I will bring all the exponential terms are on one side. So this would be 2 to the power of t by 5 is equal to 1 million divided by 25, right? So what is 1 million divided by 25? that is 40,000. So 40,000 is equal to 2 to the power of t over 5. So this is a clear exponential function. It was an exponential function, but this would be the format of the step 1, where we discussed about guidelines or stepwise algorithm to solve an exponential function. We completed step 1. What was step 2? We have to apply log on both the sides. So that implies log 2 to the power of t by 5 is equal to log of 40,000. Correct? So this implies this can, applying the laws of logarithm, we get t to the power of 5 times log of 2 is equal to log of 40,000. Okay, so this implies t is equal to log of 40,000, okay, divided by log of 2 times 5. So using a calculator, log of 40,000 would be 4.6020, okay, 596 something, you get that. So divided by log of 2 will be 15.2871 or something. Okay, so this would be approximately that 15.2878, okay, times 5. So times 5 would be approximately 76.439 or 438 hours. Okay, so the time that it takes for the number of bacteria to raise to the number of 1 million, we get the time is 76.438 hours. So this is the solution. So now you got to know how to model it, like how to model the exponential functions to find out doubling time or growth of any population. So you can do the same for any population for that matter. You can do it for any species, animal, bird, or any species population, human population also. So I will give you a quiz problem. So quiz 4.6.1 would be, you have to solve number 4. Okay, and I will end this video here. In the next video we will discuss about relative growth rate. That is, we compare one growth with the other. That is, express the growth of the population maybe with respect to time or with respect to some other rate. Yeah, it would be totally with respect to time or with respect to any other physical quantity also, like maybe with respect to the area of the vessel or with respect to whatever. So the growth will depend on many factors when it comes to real life problems. So we will try to relate it and express it as a rate of growth, okay, proportionately, and we will establish a model accordingly and solve certain problems. I will see you soon with exponential growth models for where we use relative growth rate. Thank you for listening.